Thank you. Hello, everybody. Welcome to Serverless Latency is a Thing. Today, we are going to see how best practice applied to a Lambda influences the scalability and latency of the applications. I am Daniele Frasca, AWS Community Builder. You can find me on Twitter or X, all around, working at ProSiebes at Times Media, is Germany. We are based in Germany, is a TV. This is our daily usage of AWS resource. I contribute on the 340 million invocation with the Lambda. Today, with me, there is Luca.
Hi, everyone. Probably you saw me this morning on my talk on Lambda Under the Hood. If not, I'm a principal serverless specialist. I'm based in London. Yeah, today I'm here because I need to substitute a colleague of mine that couldn't come. So if sometimes I look weirdly to him, it's because I'm looking for some tips on how I should say certain things.
Yes, the slide, you saw the slides now for the first time, so keep this in mind. So the agenda is very simple. We are going to see some basic of the Lambda. We are starting with requirements. And we'll go through some example. We'll show you some data, and at the end of this talk, we'll answer one question. Can serverless really scale? So Luca will be with me and try to say yes. So the requirement is very simple. Let's say the business want to go over 10,000 requests per second, and they wish for 100 milliseconds P99. They want to save money, want to pay only for the usage. The service needs to be simple, have good performance, and communicate with other services. Well, the classic things from management. Can serverless fit this requirement? Of course, as Luca will say. AWS offering practically is two things. AWS taking care of scalability and availability, and we putting together all these services to solve complex issues. They sell serverless as magic, scale from 0 to thousands, or is perfect for unpredictable spiky traffic. But they don't tell us that all these services have some integration latency, and really it does not scale, out of the box at least. If you are going over the quotas, you will have a lot of issues. And this actually brings us to the best practice and the latency. When we talk about latency, it's the time of the request get processed from start to the end. We can use some AWS services like CloudFront and Global Accelerator for API accelerations. We can use API Gateway, Function URL, Application Load Balancer. Until here, we cannot do much, right, as a developer. The only things that we can do is the computational level, the Lambda level. And here now, the basic from Luca.
Thank you. So as you know, we discussed this morning a bit about how Lambda works. I left aside the concurrency part because in this talk we are going to cover it. And vast majority of the time when you think about Lambda concurrency, what you need to think is that the moment that there is an invocation for a Lambda function, the first part is the initialization, that as you can see there in green, and then there is the actual execution of the code. Now, during this period of time, Lambda can handle just one request per time. So that is completely busy. So if there is another request that is coming in, we need to look into a new execution environment that is spinned up. So in this example, for instance, we have one slide behind. We have our free requests that are coming in. So we have free execution environments, free sandboxes that are spinned up, free initialization, therefore, and then the execution. Now, slightly later, we start to have more requests coming in, and because these free execution environments are still busy for serving the request, then we spin up other 2 additional execution environments for a total of 5. Now, at this time, there is a new request that is coming in, but the first execution environment has ended and respond back to the requester. So in this case, we don't have to spin up another execution environment, another sandbox. But what we do is just literally executing the code inside your handler. That's usually true for all the other requests. So now the initialization is not there, so you have what is called a warm start, and you just cover the execution part. So the cold start is not there anymore, and you start to just smash request after request after request. Now, when you think about how to calculate the concurrency requirements for your workload, you should think in this way. So in this example, for instance, we have 10,000 requests per second, and you have 1,000 1 second of response time for your Lambda. So you should be able to handle up to 10,000 concurrent Lambda executions. And then when you reduce this response time and you move to half a second or even 100 milliseconds, obviously you will have less concurrent sandboxes that are going to be spun up. And that is beneficial not only for the response time, because now you have way less cold starts, and therefore you don't have the initialization, etc., but also for your end-to-end cost of your workload. And therefore, when you think about where you think about transaction per seconds, you cannot always think in the same way like you would do with containers and virtual machine, etc., where you start to look into transaction per seconds and you say, okay, so I can handle this amount. But you need to look at the execution of your Lambda as well, because 1,000 requests per second doesn't mean 1,000 execution environments at the same time. What it means is that it depends from your execution time, and you are going to have your math that will allow you to identify how many execution environments you will have. So in this example, for instance, we have 1 second of response time, and therefore you are going to have for 10 requests 10 execution environments. But if you have by half the response time, then suddenly you can handle more transaction per second. And that is why this morning, when I was talking about Lambda under the hood, I highlighted very heavily the importance of looking into code and the importance of looking at the size of your bundle and how fast it will respond. Because the more, let's say, the faster is the execution environment response time, the more transaction per second you can handle. Now, when we look into, let's say, the Lambda concurrency, we need also to think about quotas. And that is another thing that is for every single serverless services, not just for the Lambda function. But in case of Lambda, we need to think about this part where the concurrency quota that are available on a region by region base, where we have 1,000 by default. Obviously, this is a soft limit, so if you need more, just request an open ticket to the support team. They will, based on your request, accommodate what you need. Obviously, if you don't ask from 1,000 to 1 million, because then, for justifying that, it can be challenging. But if you start to think about from 1,000 to 3,000, that's pretty smooth, right?
Yeah, it's given.
Perfect. And then the other thing that you need to think about is another limit, that is the burst capacity, that is slightly different from the concurrency. So concurrency means that you have, let's say, a certain amount of concurrent environments that can be run inside your account. Now, when we talk about burst, is how fast this environment can spin up. Because also if you have, let's say, a concurrent execution for a specific account of 10,000, can you spin up 10,000 at the same time?
No.
Perfect. Because there is the burst concurrency. And the burst concurrency is the other limit that matters a lot when you're designing your serverless workloads. Because, for instance, you can see the region where you are deploying your workloads matter. So in the case of Ireland, North Virginia, and Oregon, you have 3,000 burst quotas that are available out of the box. And then you can have 1,000 in other regions, and by default it's usually 500. And when you have consumed these, you have like an incremental 500 that are added every minute to your account. Bear in mind, all of this very recently we published that is becoming a soft limit, so you can request to increase this limit. So now let's look, for instance, this example, right? So we have this workload where at 8 p.m. has 1,000 requests. So spin up the application. It is using 1,000 on concurrent execution environments, and this one is, if I remember well, was one of the Ireland or Norwegian or Oregon. So we have like 3,000 of potential execution environment, burst capacity out of the box. Then we start to have like a spike of traffic. So we have like other 1,000 that are immediately served, but 500 start to throttle. And what does it mean? That is that you reach your first limit of burst capacity. So yes, you have more concurrent environment, but the burst capacity, so how fast we can spin up sandboxes for you, it arrived to a limit. A minute later, that 500 are capable to be, let's say, executed, and therefore it means that in your clients, when you are designing the consumption of this API, you need to think about, for instance, retries or exponential backoff. All the kind of jittering, all the kind of practices that we are used to do engineering-wise for providing the possibility to retry with a certain delay towards your API. Then obviously we start to have the capacity that now increase up to 2,500 and for the burst capacity, and then slowly but steady is going to go up to the limit that is set for your account. That is usually what you think. So remember, the important thing to let's say capture here is that you have different quotas. The concurrency means how many sandboxes you can have at the same time inside your account. But the burst means how fast you can use these sandboxes inside your account. So those are two different quotas that you need to think about, and that should help you to, let's say, design and model your traffic into your serverless workload.
So we finished with the theory. So now we'll see if it's actually serverless really scale, right?
Always.
Yeah, of course. So let's imagine you have these applications, right? Built in Docker, it works. You do 1,000 of things there. So at some point you want to move this architecture to serverless. You do your research and you find something similar to this, okay? So this is just an example. I just put all the services to show you how bad is the integration latency within the services. So this is our microservices, a super fat Lambda. And we start testing, right? So AWS asked me to call each of my users. I say, look, please come 1,000 per time, because this is how we want to scale. So only 1,000 per time. So my users all very educated, and come 1,000 per time on my website, right? So we did this test, and we got all the metrics with CloudWatch AMF. This is because there are no observability tools that tell me how much is the integration for each of services. One of these, like EventBridge, doesn't even have metrics. So I pre-calculate all of them, and I will show you on this, and I will show you for each of these best practice. So we start serverless. I do not know anything about serverless. I just translate the same code to the serverless and deploy. So this is the worst case scenario that you can do. And this is the results, right? So as you can see, the worst integration latency that you can have usually is with EventBridge, step functions, and S3. So remember always this. So Luca told me that serverless is magic, can scale from 0 to 1,000. So, wow, I need to reach my 10,000. I go and do some load testing. I do the calculation with the transaction per second, and I see already that I cannot really reach the 10,000 requests per second. But I say, okay, let me load testing. So I do a load test, and nothing works.
Yeah, so you mentioned that you have a fat Lambda, right? And probably you have some integration through the SDK, considering that you're using that Lambda for sending messages to different services. Therefore, I presume that at some point around 2,300 and 3,000 requests, you start to have some issues and bottlenecks. or the SDK start to throttle. Because our services obviously cannot scale infinitely, you need to design the way that will allow you to do that. But have you ever thought to, instead of having the SDK and initialization for all the services inside the handler that is executed every time, moving it outside the handler?
Of course. In fact, he tell me one best practice per time, so I spend other hours to change everything, and I do the second case. And I say, oh, wow, now my Lambda is slightly faster. So I'm sure that now I can reach my 10,000 requests per second. So I'm going to check still, I cannot really reach that quotas. And when I do load testing, it's even worse than before. So how come?
So when we were in the call, you showed me the code and you started to call sequentially every single service. But do you need to wait when to receive, let's say, the acknowledgement from SQS or SNS or even Bridge before moving to the next one? Maybe looking into parallelism will increase your throughput.
Well, so again, they tell me one thing per time, so I go there and try. Now I do parallelism, right? So, wow, now it's much faster. So 22% faster than before.
You see?
So, yeah, you see? Luca knows the stuff. So I'm going again. So theoretically now I can reach my 10,000 transactions per second. So I'm going to load test again. Weeks are passed, and all of this. I have nothing to do. And still failing.
Let me see. So this one is the concurrency, the throttling. Okay.
So yeah.
So on this case, what was that?
So practically we have the SDK still
yes.
giving us errors and the throttling.
Yes, so the SDK is still giving you the error because we have seen later before that there is this potential limit between 2,000 and 300, but then you have also errors on the downstream services that could come. And therefore, you need to figure out maybe a better way to, let's say, independently call these services. Have you ever thought about the outbox pattern, for instance?
So here we go again, right? So every time there is an excuse. So serverless magic doesn't really work. So now he asked me to refactor completely my applications. So we go into the single responsibility Lambda. I apply the parallelism, I apply the execution context to reuse all the connections. And theoretically it works. So in fact, in terms of latency, everything works. Now I can do 140,000 transactions per second as maximum peak. So that is quite great, right? But what is the issue here? Anyway, synchronously having Lambda in this way.
Yeah, the challenge here, it seems that there is DynamoDB latency. So it seems that, for instance, when you set up your DynamoDB timeout, you keep like a very short timeout. I know that is 2 minutes currently the default one, but maybe you can find a sweet spot between 50 and 2 minutes, right?
Yeah, so, but the issue actually is, even though now I'm asynchronously and I can do all of this, all what AWS tell me, the issue is my user still need to be very educated. I need to come 1,000 per time. Because if they're coming a group of 2,000, what's happening in this scenario?
And you have like the burst traffic that could kicks in and then start to throttle.
Exactly. So again, Lambda doesn't really scale because you always have the next issues, right? So this is yours.
So let's look to a few best practices on the synchronous side. So what we mentioned is first load testing. Load testing is your best friend. So especially with serverless, you want to understand and model your design, your architecture in the way how your, let's say, traffic pattern looks like. That is the key thing. Understanding how the traffic pattern works will allow you and will enable you to design serverless application properly. The second thing is set appropriate timeouts. So usually, there are some default timeouts that we set, but it's not necessarily the right one for your workload. Sometimes having a faster timeout will allow you to, let's say, make changes on your clients calling your API and make your life way easier. Then, as I mentioned before, your clients should know that when there is a certain type of error, they should retry, and should retry with exponential backoff. So that will, it's a classic technique you can find also in the builders library that is suggested by our principal engineers for handling this kind of workloads. And last but not least, bear in mind that it could happen that the client is misbehaving or is doing something that you don't expect, and therefore you can make a request multiple times. Idempotency is a technique that will allow you to maintain the same ID when the request is not fulfilled, and then you can identify if the request was fulfilled and discard the new one, and therefore you are sure that the response, or better, the execution of a specific action happened just once and not multiple times. But at this stage, so here you can dive deeper on a few things. But at this stage, my question for you is, have you ever thought about asynchronous programming and started to look into synchronicity?
Of course, right? So synchronous doesn't work, all the best practice do not work. Now I need to change everything in asynchronously because the world is asynchronously, right? But I still need to send a response to my user. So but for AWS, this doesn't count much. So we are going in the world of asynchronously.
Exactly. So what we have done here is a very simple test where we have a Lambda function, one of the services that are listed over there, and another Lambda function as consumer. And as you can see here, there are, so the best one on all these services that performance-wise is definitely SQS. But there is one thing that stood out. That is, for instance, SNS SQS, that is quite a common pattern in many of our, many of our customers. It is faster than using just SNS. Why that? Because if you're using SNS and the Lambda as a consumer, as I mentioned this morning, this, let's say, event is going to be picked up by the front-end service inside the Lambda service, stored inside the queue that is shared across all the customers, and then it will start to drain. Instead, if you have a queue that is only your own queue, then it becomes to perform faster, because then it will be on your account, inside your account. It's not, let's say, shared with anyone. It's just your queue, and you will be able to drain from there in a faster way.
So you take all in account all of this best practice, everything asynchronous, everything. So I just show you quickly the three cases, EventBridge, SNS, SQS. They are pretty much behaved in the same way. So it's just to see the integration latency. As I said before, remember that my requirement was to return a response to the user under 100 milliseconds, right? So look at this one with EventBridge. API gateway to EventBridge, 166 milliseconds. EventBridge, SQS, Lambda, 300. So I'm already out of the requirements. And plus, because now we are on the asynchronous world, as AWS really wants, we are going inside the issues of the WebSocket. There are three different implementations in AWS: API Gateway, IoT Core, and AppSync. They are all three different, but in this case, I use IoT Core thing because I need to send the WebSocket to a TV as well, right? And so, just to show you very quickly that more services you are using, higher is your integration latency. And, but the services make a difference. SNS, for instance, as just Luca said, is much faster than EventBridge. And in the end, of course, SQS in my test was the fastest of the three. This is because there are less services in the middle, right? So less services you have is lower your integration latency. And so, in fact, I can reach almost 20,000 transactions per second. And of course, with this step scaling, load testing, I have no problem. I can go to 20,000, 30,000 requests per second, and up to the limit of the API gateway.
Yeah, there are a few also learnings from here, right? Thanks. So first of all, using asynchronous invocation helps you a lot for scaling. And the reality is, what I've seen also in the trench is that very often we design things synchronously, but there is no value on doing that. The other cool thing of moving asynchronous is that you can leverage batching. That will have a direct impact also on your cost at the end of the month, because instead of having every single request processing one by one, you can say, okay, I want to process these 10 things all in one go, and then it means that one execution of a Lambda function is going to take 10 messages and start to do whatever operation you need to do. That is great. It's also possible to catch errors. You can use, let's say, the Lambda destination, that is a functionality to decide how the things are going to, let's say, be called in the case that you have like a failure or a success. So also in that case, it's built in this capability inside Lambda to say, okay, now I want to, after that I did a specific action on a batch of messages, I want to call, let's say, I don't know, SNS or another service that is integrated out of the box. And then you need to make sure on the metrics that they are remaining at or close to zero. So you have a lot of, let's say, possibilities with asynchronous workloads, and more can be on best practices can be found at this URL here. The other thing is that you need to bear in mind that Lambda has, let's say, some optimization that you can apply straight away. So small packages is one thing, because the first thing that we do when we have, let me see if this one works. Yes, fantastic. So when you have like, at the beginning when you invoke a Lambda function that is completely code, we are going to download the code. Obviously, if you are creating like a Lambda function with containers image of 10 gigabyte, it takes slightly longer to be loaded, obviously. So the cold start is going to be bigger. And it's similar for when we talk about execution context. So you can leverage the initialization phase of Lambda because you have the possibility to. So for instance, if you are calling parameter store or secrets manager and you want to store for the entire execution environment for the entire life cycle of the execution environment, this information, you don't have to ping every single time from the handler like Daniele was doing, but you can start to have that with one call, and you don't overwhelm even the system. Potentially, you can also think to use an extension. There are some extensions available for Lambda function that will have the possibility to set time to live on this caching layer. And in this case, when the time to leave expire, they're going to make the next time a call to parameter store or secrets manager. But as you can imagine, you don't have to handle all the logic for doing that because this extension is created and managed by us. You just need to plug into your Lambda. Another thing that you should think about is, working? Yes. Is avoiding the fat Lambda, and there, there are different school of thoughts. I think it depends from what you need to build. Ideally, as I was saying this morning, trying to start with coarse grain, let's say split of your logic, and then starting to go more fine grain when time comes. Because the reality is, for instance, very often your workloads will be optimized for reads more than write. Then obviously there are some workloads that has to be optimized for writes, but the reality is you can start to, let's say, design your Lambda function even splitting in two. That will enable the possibility to use CQRS. That is a great pattern because you will design the scheme of your data for read only or read mainly, and then you have a completely different way to structure your content on writes. And also, if you have like a read-heavy traffic, that specific Lambda function will be hit faster, so you can have, let's say, a design that will reduce the response time and therefore can handle more requests per second. The other thing is cache. That can be done at the TMP level, but it can be done, as we have seen at the initialization phase, or it can be done with additional, let's say, possibilities that Daniele is going to show us in a few seconds, and use parallelism when possible. Because very often we think, oh yeah, we need to wait for the acknowledgement of this service and that other service and so on. But in reality, we don't. We just need to make sure that we fan out their request and everything will work out of the box, right?
Yes.
Of course.
So in the end of the day, right, the best practices are there for a reason. So as you can see, if you remember, the requirement was 10,000 requests under 100 milliseconds. It's pretty much impossible. That's it. This is the conclusion. It's impossible, and it's always a trade-off. A synchronous request, in this case was a post, but you cannot cache a post, right? So you need to find a way to make it work at scale. The only way to make it work at scale is going asynchronously, right? But you need, if, like me, you need to send a response to the user, you need to find a way. And the way is IoT core, so the WebSocket, or there are different type of partners that I will avoid to that. As you notice here, the last row, there is Rust in the middle, because you are asynchronous, but still, I was running around 350 milliseconds. A response is quite a lot. So the last best practice that AWS tell you is, you know what? You are using the wrong runtime. Use a better one, Rust. Rust is the fastest of all. And as you can see, from around 150 milliseconds, you go down to 60. And you also cut the response time to your user of 150 milliseconds. So keep this in mind, that they will ask you to change everything at some point if you are looking after the speed. So until now, we show you the case of a post. But what if we need to do a get? No? The get is simple, but you cannot do synchronous call without caching. Serverless will always crash, but it will crash only because...
Always is a big statement.
Yeah, always, if you are going over the quotas. The quotas that they give you are for hello world applications, right? So I'm working media, I'm building like streaming applications and everything. I do 1,000 requests per second, I don't know, when nobody's on the website. So anyway, it doesn't work, right? So you go synchronous, get how you want to do it. So the best practice is caching. You can cache at any level. You can cache on front of the API gateway. You can use a CloudFront for that, a CDN, just for caching for a few minutes. You need to work with eventual consistency, but this will allow you to go over the 10,000 requests. You could cache at the API gateway. Good luck for that. Nobody do it. And so you will end up to cache a Lambda level. And for this, you will probably use Elastic Cache. And once you move with Elastic Cache, you need to have the Lambda inside the VPC. So now you're losing the power of serverless, focusing on what really counts, features, developing features for your user. Now you need to think about networking. The price will go up because now you need to have a NAT gateway. You need to pay double your data transfer, all these kind of things. So Elastic Cache is there, it works. You don't know how much big the cluster for Redis you need to set. So you will do like everybody, over provision. And you will just pay €1,000 every month just in case. But what is the issues with Redis? Redis is famous to have issues when scale up, down, failover, adding replica and everything. At that point, you will have what is called cold cache or cache avalanche. That means that because you will have a miss, you will hit very hard your downstream services. So be careful when someone will tell you use Elastic Cache. Luckily for us, there is an alternative, and the alternative is called Momento. I don't work for Momento, so they deserve the honor to be mentioned. Momento is a serverless cache. So at this point, you don't need to put a Lambda inside the VPC. You can keep working and focusing on what you're usually doing. They have a drop-in library that you can use, the same code of Redis and everything, all work. And it's serverless. So they take care of scalability for you. And even if you're paying the data transfer to Momento, this will always be cheaper than having a Lambda in a VPC because you will going to pay for the NAT gateway. I did some tests with Momento. and I reach 500,000 requests per second. So 500,000, I think, is good enough for everybody. That's it. So the thing is, can serverless really scale?
Of course, with some trade-offs.
It depends. It really depends. The issue is load test everything. Make sure that you are aware of the quotas, because all the AWS services are different quotas, different standards. So at the time that you are out of the hello world example, you are in trouble. It works. I reach 30,000, 40,000 requests per second. No issues asked. You ask AWS to change the quotas, you make it. But don't do the mistake. Try, fail, and go back to the cluster. Because anyway, even with a cluster, you'll always have the same issues. So load testing and knowing what you are doing is very important. Best practices are there for a reason. And with that, we finish.
All right, I think we've got time for just one or two questions, if there are any.
Yes, we are Italians.
Do you have any recommendations for testing serverless architectures?
Testing, what I do is I use Scala. Practically, I create the test case with how many requests I want to reach, and I spread on spot instances. So I create 10, 20, 30 spot instances and hit the endpoints with different issues. And after I go to Luca and his team complaining. So yeah, so this is how it works.
Awesome, cheers.
Well, thank you both very much. Just one final.
Thank you.
Thank you.